Start again, and we're going to have Joshua Norton from the University of Illinois at Chicago. He'll take us through till about 5 o'clock, and he's going to discuss why he has no time for problems.
Right. So you might think, given the context of this conference, that my topic is on the problem of time. That's actually not the case. I was actually hoping by being at the end of the conference that there'd be no time left to cause problems. There might be more time pun jokes coming up. I am going to be talking about the problem of time and loop-quantum gravity, and as Daniele kind of already started us on the topic from, it's weird, from, there we go, it's kind of fun, right? Zoom in and out. So Daniele already started us on some of the things that we talked about, and I didn't actually set up the talk this way, but since we ended with his, I thought I might as well jump into kind of foreshadowing what it is that I'm going to be discussing. So under Rovelli's interpretation, and as Daniele himself also endorses, there's no time in loop quantum gravity, or in some understandings of what's happening in loop quantum gravity. And in particular, there's no space either. And by what Rovelli means by this is it's not that there's no time or space, but there's no manifold. All we have is the metric. Now, under that conception of what time and space is, and maybe what we mean by emergence as well, we've lost some of the structure that we've used to interpret what our constraints are in loop quantum gravity. So in particular, when we interpreted the Hamiltonian constraint, there was this time variable that we said our dynamics was frozen with respect to. There's some structure on the manifold that we interpret our vector constraint with respect to. There's these spatial diffeomorphisms. But the manifold isn't physical if it's not space. We're going to wonder what our interpretation of those constraints should be. And so that's kind of the thrust of some of the things we're going to be talking about. Now, time is going to go missing in different versions of space-time emergence that have nothing to do with the way Rovelli gets rid of time and space. Okay? So we're going to go through, well, I'll just go through the introduction because I'll hit that. Okay, so as I just mentioned, I'm going to be talking about basically the problem of time and how it relates to our constraints and how it relates to our interpretation of space-time emergence. I'm going to talk about 4 different families of space-time emergence. And now, by family, I might sometimes say 4 different families of interpretations or accounts of space-time emergence. I really mean these to be sort of synonymous expressions. And when I say the problem of time in loop quantum gravity, I'm really thinking about only this, the problem of time that's generated by our interpretation of the Hamiltonian constraint. This idea that we have some frozen dynamics and that we're going to interpret this in some way or another, that time has gone missing. Now, time will be missing in some of the things I talk about, but it has nothing to do with the problem of time as it relates to the constraint. Okay? So when I say the problem of time, or if I say there's no problem of time, it's because it doesn't relate to the constraint in particular. Now, you might still say, oh, there's still a problem, and there might be, but I'm going to kind of give us an interpretation of that, which makes us, it'd be disingenuous to keep calling it a quote-unquote problem. And we'll talk about that. Okay. Oh, no. It's doing too much. Okay, so the structure is that we're going to talk about the Hamiltonian constraint. I'm going to motivate it a little bit. I'm going to give us a prima facie conflict between the Hamiltonian constraint and some interpretations of space-time emergence. I'm going to go through 2, I said I'm giving us 4 families of interpretations. There are 2 that are physics-y and 2 that are philosophy-y. I don't know if I'll be able to get through all 4. I'll choose, depending on how fast I talk. And now I'll do some concluding remarks. It's kind of fun all zooming in. So in loop quantum gravity, this is pretty familiar given the different talks that we've had today, but we formulate general relativity in terms of a Hamiltonian constraint. What this means is that at the end of the day, all we have in terms of our total Hamiltonian is a sum of constraints. There are 3 of them, given Ashtakar's formulation of it. In order for us to build a physical space of states, we require that their states are annihilated by each of these constraints. These constraints are then given geometric interpretation. The gauge constraint requires that our states are invariant under gauge transformations. The vector constraint requires that our states are invariant under spatial diffeomorphisms. And then this quote-unquote scalar constraint is the one that's going to generate our problem of time. Okay? The scalar constraint is also called the Hamiltonian constraint. It's said to govern our dynamics. And as we'll see, if the state if the operator annihilates our constraint, our state, then we're going to say that the state is invariant underneath time translations. Okay? So there's, in a sense, we'll see, there's going to be no dynamics in our theory. And that's going to be a problem. Now, oftentimes it's the case, oh, there it is. That's a Hamiltonian constraint. You know, we often see the H here. You often wonder what the H means. We're going to get to that in a second. In order to generate the problem of time, we need to be convinced that the scalar constraint is the one that's governing our dynamics. Now, I'm going to give us a little bit of a story for why we ought to think that's the case. This story is only a heuristic. For the time being, we don't have time to go into more detailed analysis. But the reason why I'm giving this is just because you put an H here, it doesn't mean we need to automatically assume it's telling us about dynamics and time. Usually, in a Hamiltonian system, it's the Hamiltonian itself. In a Hamiltonian-Jacobi system, I guess it's the Hamiltonian constraint. But one often wonders why it's not the Hamiltonian itself, instead of just one of the constraints. So with respect to GR, we're going to go ahead and discuss why it is that we're talking about this third constraint, the scalar constraint, as governing time evolution. That way we can generate the problem of time. The sort of heuristic I'm going to give you comes from DeWitt's, I think it is 1963 paper. So this is not my story, this is his. So if you look at the way DeWitt wrote out this constraint originally, it is written in terms of this. This is your extrinsic curvature. That is your intrinsic curvature. In GR, the energy of our system is encoded into the curvature of the manifold. And so in a sense, we've got two different energy terms. You've got an energy term that has to do with the extrinsic curvature, and one has to do with the intrinsic. And this is like a k squared. This is like a k squared term. This is like a kinetic term. And so DeWitt's like, okay, so you've got like a kinetic energy curvature term here. You've got a potential intrinsic curvature energy term. This is encoding the energy of the manifold. And so if any of the constraints are going to govern time translation, it's going to be this one. This is where the energy is stored. So DeWitt says, okay, that's cool. But here we have a problem. Now DeWitt talks about, he doesn't use this, he doesn't call it the first problem of time. I'll call it that. But we are able to generate the frozen formalism. I believe Tom mentioned the frozen formalism at one point. Did you, Craig, as well?
Yeah, I think so.
Okay. Oh, whatever. It's mentioned all the time.
I think about it sometimes.
In quantum systems, the physical information of our system is encoded in terms of inner products. In the Heisenberg picture, we have these operator inner products given like this. So here is our metric. We put a little hat on it. It's now an operator. And then we sandwich our two states in between. Again, LaTeX doesn't work very well with Prezi, so you have to take pictures. DeWitt says, okay, that's cool. This is where our physical information is stored in these inner products. However, it's going to be the case that for any time, future time x naught, if our state gets annihilated by this constraint, then it's going to be the case that our inner products are going to be invariant over time. So all the physical information when we get out from our states are going to be independent of when we kind of measured those things in time, or as we evolve them in time. The physical information is not going to change. And so according to DeWitt, what he says is, okay, this is a problem. This is what I'm calling the second problem of time. No time, there's no time in the theory. Now what I take DeWitt to mean, we're going to see in the next slide, he actually quotes what he means by there's no time in the theory. What he means is the x naught, the coordinate with respect to which we were trying to evolve our geometry, it can't play the role of time because there's no dynamics with respect to it. In fact, the same story is going to be told for DeWitt with respect to also the spatial coordinates. We're not going to get any variation as we move our spatial coordinates around. This is DeWitt. He's cool. He's hanging out, maybe in this room. He had some thoughts. He says this. Instead of regarding this equation as implying that the universe is static, we shall interpret it as informing us that the coordinate labels x mu are really irrelevant. Physical significance can be ascribed only to the intrinsic dynamics of the world, and for the description of this, we need some other kind of intrinsic coordination, etc., etc. Oh, it's 67, not 63. Okay, so what he's going to do is he's going to say, look, our coordinates aren't going to be able to play the role of space and time. We need some other structures. Some people define structures on the manifold as being functions of the coordinates and maybe functions of the metric and maybe functions of other matter fields that try to build clocks and different things to build time, what's going to represent time. As we're going to see, there's another thing you can do. You could actually throw away the manifold altogether. Now, DeWitt at this point hasn't done that. DeWitt's just made the claim that these coordinates aren't able to play model space and time as we usually have thought them to do. Oh, I could have done that earlier. At any point in the talk, if you want me to slow down and restate something, I mean, it's the end of the day. We might as well just have a conversation if you guys want to talk about things. If you have a destructive comment, you can save that to when my talk is over and the comments are over as well. And you can find me privately in the hallway. Yeah.
This is exactly the relational time idea.
Yes, no, exactly right. Yeah, this is exactly the relational time idea. Yeah. All right. So now we have the idea of what we mean, what the problem of time is and how it comes about, our two senses of it. I'll refer to the first sense, or the first aspect is frozen formalism. The second one is time has gone missing in some sense. I'm going to now show that there is a prima facie conflict with at least with how space-time emerges and how it is that we've come about in discovering this problem of time. All right? I'll go through first some things by Rovelli, and then we'll go through other accounts of space-time emergence. So here's Rovelli. He's very happy. He's in France, I guess. Got some thoughts. Maybe this will zoom in. Oh, good. Okay. So Rovelli will say the quanta of the field. Okay, so our spin networks are going to be representing the quanta of our field. And he says they cannot live in space-time. They must build space-times themselves. Physical space is quantum superposition of spin networks. A spin network is not in space, it is space. And in particular, spin networks aren't in time, they build time, okay? Now technically they aren't time, right? Because time is supposed to be a classical concept, but he doesn't mean it is space, he means it's like a quantum version of space, and out of these things, space will emerge. Okay, but let's think about this. So if our states are in space, or time, if they build space and time, then what were we doing when we were interpreting, h hat on our state? And we were interpreting this as a dynamical equation. We're interpreting it as evolving our state in time. But here we know that space and time are emergent structures. Then how is it that we are interpreting the Wheeler-Dewitt equation that's describing evolution in time? So there seems to be some prima facie conflict. Now I'm actually going to resolve this conflict with respect to Rovelli, but there are other accounts that there isn't going to be a resolution towards. Daniel.
What do you ask the question in the quantum setting? You can ask it in GR.
No,
You
surely.
write the equations in phase space, and you have a constraint, and you have a...
Yeah. So what's going to be interesting about...
It's totally different.
It's not. Yeah, so what's going to be interesting about a lot of things I'm going to say on behalf of Rovelli is you can say all these things in a classical setting as well. So actually probably 2 slides from now I'm going to say just that. I don't know just that, but roughly that. So do we see that there's a prima facie conflict between the previous derivation of the problem of time and then what it is that we take our states to represent? Space-time isn't there. This represents pre-spatial temporal structure. We had used the manifold in defining the problem of time, so this seems to be some problem. There actually won't be in the case of Rovelli, but for these other notions of emergence there will be. Okay, we talked about this. What's the deal with Ham constraint? Okay, so we're going to talk about 2 different families of interpretation for space-time emergence. One is this Rovellian one, and then one is TG. I'll get to TG in a second. So with Rovelli, he's going to say there is no manifold, there is no time. Okay, and this was was referenced in the previous slide, but I'm going to unpack that for us. Okay. You know, I was looking for a funny picture of Rovelli. Huh?
Happier and happier.
Yeah, yeah. I was trying to find a funny picture of Rovelli, and someone already did this. You know, presumably he didn't have a bunch of fireworks behind him. Someone else put fireworks there. Okay, so Rovelli's like, I got some more thoughts to tell you about. Okay, what I want us to do is read the bottom quote first, okay? So the bottom quote says, oh no, close your eyes. I want you to see this. Okay. Okay, so I want to go back real quick. So, as Daniele mentioned, the same story happens in classical general relativity. And this is as follows. If general relativity, as we know, is invariant under four-dimensional diffeomorphisms, which means we can move things all around. Okay, in the philosophical setting, this comes up in what famous argument? The whole argument, right? Now, the whole argument tells us, well, we're not supposed to reify the points, right? They all mean the points. There are no points of space-time. Perhaps there's no space-time manifold altogether. Maybe the topological structure. Rovelli takes this point very seriously in his halfway through the whole Woods article, as well as in his 2004 book. He mentions, look, if the manifold isn't showing itself in any sort of way, then it's just going to be pure gauge. We can gauge out over it. The manifold doesn't represent any physical degrees of freedom. Okay? There is no space-time manifold. There's just a space-time metric. Okay? So that's one view that we could have. Now we have to be careful because we're about to quantize this structure. We want to make sure that the same arguments we had classically are still around when we quantize it, right? So now we have a quantum theory. Does that same argument hold? Well, when we do loop quantum gravity, we take a four-dimensional space-time. We do a 3+1 split. It turns out that how we do that 3+1 split doesn't actually matter. So you do three-dimensional spatial slice, one-dimensional quote-unquote time slice. Doesn't matter how you do that. Your vector constraint tells us that the physical data should be invariant as we move it around in three-dimensional spatial diffeomorphisms. The scalar constraint says that it shouldn't matter how it is that you evolve this system or scale this system in time. Okay, so it doesn't matter how it is that you do this 3+1 split, and then once you do it, it doesn't matter how you move all the data around. Okay, the physics should be the same. So what we see then, in the context of loop quantum gravity, is we've taken the four-dimensional spatial diffeomorphism invariance of GR, and then we projected it in three different ways. First, in that it doesn't matter how we do the split. Second, in that you get the three-dimensional spatial diffeomorphisms. And then third, you get this one-dimensional time quote-unquote diffeomorphism. All right? So this sort of freedom, this sort of gauge, quote-unquote gauge freedom that we saw in general relativity and GR is present in the quantum gravity, in the loop quantum gravity context as well. It's projected in these three aspects. So we could provide the same sort of argument. We could say, look, the manifold isn't showing up in any sort of way. It's playing no role in making predictions for our theory, so throw it out. It's just gauge. Those aren't physical degrees of freedom. This is what's radical about it. When we take this seriously, there is no manifold of space-time. There's only a metric. And so you'll hear quotes by Rovelli saying, you only have fields on fields. He talks about these ideas of animals on a whale, and you think, oh, the animals are on an island. And you get closer, it's just animals on a whale, so it's just animals on animals. You have fields on fields. That's all there is. I know. Yeah. So let's go ahead. I think I'm ready to show you. Let's go ahead and read what he actually says. Okay. Okay, reading the bottom quote. In fact, M, the space-time manifold, has no physical interpretation. It's just a mathematical device, a gauge artifact. There are not space-time points at all. The Newtonian notions of space and time have disappeared. The space-time coordinates x and there's a t over here. Have no physical meaning. Okay, reading the top. Now note, there's a sense in which even DeWitt wants to say that this is true. X and t don't have a physical meaning, right? That doesn't mean that you have to de-reify the manifold, right? That's a further step, and that is what he will do. So what Newton called space and Minkowski called space-time is unmasked. It is nothing but a dynamical object, the gravitational field. The gravitational field is the same entity as space-time. So when Rovelli talks about space-time emergence, he isn't talking about manifold emergence in any sort of way. He's only talking about the metric field emerging, or classical spacetime as seen from classical metric. And now this is a good thing to keep in mind. My battery's low. That's a terrible.
What kind of charger do you use?
No, I've got it up there. I'm going to talk and then do this at the same time. You want to be in my bag? Okay, so when Rovelli talks about space-time emergence, he's going to be talking about something very particular, and that's only the metric field. When we talk about other accounts of space-time emergence, we're going to be talking about accounts which include manifold emergence as well. Now, as a philosopher, and I'll maybe probe your intuitions, when someone says space-time emerges, what's the sexy notion? The full, robust, manifold emergence, right? Because that's what's weird. You know, we have lots of examples where we've quantized other fields. You know, the metric field is just a special 2 form. We've quantized all kinds of different forms on the manifold before. So if we want a really robust sense of emergence, one that's unique, it's going to have a manifold coming into existence as well, and not just a different sort of classical P form. Okay? So, let's see, what's next? So I'm not done, so I want to make sure. Okay, so with Rovelli, you get space-time emergence, but you don't get manifold emergence. You only get metric emergence, all right? So there's a thinner notion of emergence that's at play, that's fine, but we should just be upfront about what we're getting out of the theory. We've thrown away space-time out of the manifold. It's no longer a physical stuff. But if you've thrown away the manifold, you've also thrown away x and t, right? And so now we need to go back to how it is that we've interpreted our constraints. There's no time in the world, there's no coordinate x naught in the world that's representing some structure in the world, right? X naught doesn't represent any structure. It was de-reified, right? So what were we doing when we interpreted the Hamiltonian constraint as being about evolution in time? There seems to be some conflict there. Now, there's no conflict with Rovelli, okay? This is what the story we tell with respect to Rovelli. Rovelli says, okay, take the manifold seriously. You take the manifold seriously, you're going to have a problem with space. I.e., you can smear things around in space and it doesn't change. You're going to have a problem in time, move things around. Okay? So if we take the manifold seriously, we're going to just see that all of our physics is gauged with respect to those degrees of freedom, so throw it away. Okay? So the reason why he throws it away, part of the reason, is because of the problem of time, or the potential problem of time. Now, the potential problem of time isn't the only reason that motivated us throwing away. There's 3 reasons. You know, the invariance as we did the 3+1 split, the fact that we have invariance over time and invariance over space. So those 3 things combined together tell Rovelli, throw the manifold away. So the reason why we don't have time in a Rovellian loop quantum gravity is connected to the Hamiltonian constraint, i.e. it's like a reductio. Take it seriously, okay? It leads to these sort of problems or strangenesses. So we're going to throw the manifold away. Okay? There's a reductio there. So there's a close connection between not having time in Rovellian loop quantum gravity and the Hamiltonian constraint. Okay? So for that reason, I'm going to say space-time emergence under Rovellian loop quantum gravity is consistent with the problem of time. Where again, the problem of time is the one that's connected to the Wheeler-Dewitt equation. Okay. Now, the reason why I bring this up to begin with is that the other 3 sort of accounts of space-time emergence aren't going to be as nicely related or related at all to the Wheeler-Dewitt equation. Okay, so this is going to be a good way for us to keep these 2 things consistent, i.e. the existence of the problem of time and having space-time emergence. The other ones are going to have space-time emergence. We're not going to be able to derive the problem of time. So in a sense, they're solutions to the problem of time. They don't allow us to derive it in the first place. Okay. Questions? Am I talking too quick? Yeah.
But again, you keep returning to the Wheeler-Dewitt equation, then
Yeah.
constraint equations, and that exactly the statements of Carlo there. I mean, are statements about classical GR.
Yeah.
So why are you not bothered by classical GR and instead becoming bothered by the problem of time in loop quantum gravity?
Yeah. So I didn't mean it to
It's a
sound.
fundamental difference that gets rid of any physical reality for points of a
Good.
manifold in classical geometry. You may not even split it into 3+1, just 4-dimensional difference. The
Yeah.
whole argument is exactly that. The points have no meaning.
Yeah, I didn't mean to phrase it as though I had a problem with it. I really set this up as Rovelli's example as a way of stimulating our conversation. The other three ways in which space-time merges is going to be explicitly relying on quantization techniques. Okay, and so this one is cool because first off, well, it's cool because it's related directly to the Hamiltonian constraint or normal four-dimensional diffeomorphism invariance in classical mechanics.
So you're saying that there are other notions of
Yeah.
problems of time that have to do directly with the quantization
Yeah.
procedure.
Yeah, and I'll rephrase what you said, and that is there are other notions of space-time emergence that have to do with our quantization technique, and those are in conflict with how it is that we're deriving the problem of time, at least with respect to the Hamiltonian constraint here. Okay. Yes, I don't mean to pose that, oh, in quantum system there's something wrong with what Rovelli is doing, but it was okay with what our interpretation of the whole argument in GR. No, they're exactly the same situation, exactly the same intuition. If it is that you think gauge freedoms show you that these are non-physical degrees of freedom, the interpretation is the same in both situations. Yeah, so I'm sorry if that wasn't stated clearly. So the next one we're going to consider is TG. Now, what I mean by TG is topology geometry. And by topology, I actually mean much more than that. I don't just mean the open set structure. I really mean, when we're doing loop quantum gravity, we've quantized the metric. Some people have said, look, there's still a lot of background here. We really want background independent theory. Let's quantize more structure than just geometry. Let's quantize the topology, the differential structure, the sort of base set of points from a continuum to maybe forcing it to be discrete, etc. Okay? So there are some explicit accounts of how people have done this. Chris Isham has worked on this. He talks about this. Him and Jeremy Butterfield talk about these notions in their 2001 paper. Isham talks about different ways you can go in terms of quantizing more than just the geometry in like geometrical and philosophical conceptual problems and quantum gravity or whatever. So there's a reference there. So Isham talks about how you could go beyond just quantizing geometry. Christopher Dustin does this. I believe he is at the University of Florida.
Well, he was, I think, Stony Brook now.
Yeah, he might be at Stony Brook now. But his idea is basically you've done everything like you do in normal loop quantum gravity, but then you're like, hey, but we want to include some topological information. So he adds a variable there that encodes some topological information like the genus of the spatial slice or different sorts of things. Okay? So you can kind of extend loop quantum gravity so that you capture more information than just geometry. Now, if you do this, your states are going to represent not only something which is pre-geometric, okay, but you're going to be summing over topologies or some such structure as this. And if you do that, then your states are going to represent something which is even more spatiotemporal than what we had in just normal loop quantum gravity. It's more spatiotemporal because in normal loop quantum gravity, you still have the manifold there. Now, if you're Rovelli, you're going to throw the manifold away. If you're most people who came before Rovelli, there's still a manifold there. Okay, and they're still going to talk about structures on the manifold or defining things with respect to the manifold. But if you're taking this TG route, you're going to quantize more than just the geometry. You can quantize structures on the manifold itself. And if you do that, there's a good sense in which you no longer have coordinate functions at all as they're normally defined. If you don't have coordinate functions at all as they're normally defined, you don't have an x naught with respect to derive the original problem of time. Right? So if you're really going to want a really robust sense of space-time emergence and the manifold is no longer there in its normal sense, then you're not going to have the sort of coordinate functions with which we use to interpret our constraints to begin with. Okay? So that's just a little note. This is a physicsy sort of way where we get space-time emergence. It's a thicker space-time emergence because you get a manifold supposedly out of the emergence scheme. And again, you don't have a time coordinate with respect to derive the frozen formalism. Okay? So I'm going through different ways with which we can have space-time emergence and showing how there's some conflict with respect to deriving the frozen formalism. This is why the paper is titled, There's No Time for Problems. Depending on how it is that you've quantized or how it is that you think space-time is emerging, we might have removed too much structure for us to derive our interpretation of the Wheeler-Dewitt equation to begin with. So we've talked about two physicsy sort of examples. I'm going to talk about, first I'll talk about, not Jeremy yet, two philosophy examples. This one I'll come back to if we have time. I'll do this one now. It's called trickle-down effects. the idea is, with TG, we explicitly quantize the topology. With trickle-down effects, we don't explicitly quantize anything but the metric. But there might be a sense in which the effects of quantizing the metric trickle down and indirectly affect the manifold structure. Okay? Now we will enter the Jeremy Butterfield. Hey guys, sorry I couldn't be here. I'm in Cambridge. Okay. So when Jeremy, this is in Jeremy and Isham's 2001 paper, when they're talking about trickle-down effects. They talk about trickle-down effects in the context of string theory and in the context of loop quantum gravity. Jeremy says, for canonical quantum gravity program, we mentioned the discrete spectra of spatial area and spatial volume quantities, results that arguably suggest some type of underlying discrete structure of space-time itself. Okay? So again, this is in the context Jeremy is saying we started off with a continuous manifold, but we've quantized the geometry, and so there's some sense in which perhaps we only have a discrete structure underneath space-time anyway. Okay? We haven't talked a whole lot about this. I will talk about it real quickly here. In loop quantum gravity, as most of us know, we've defined things that we call area and volume operators. And these area and volume operators, they act on our states, okay? And they produce a number which is within the right sort of within the right sort of, for some states, they approximate Riemannian geometry very well. Okay, so we have some states, weave states, that that the numbers produced, when we act on them with our area and volume operators, produce very classical looking geometry, okay, areas and volumes. The problem is, not the problem, but probably what we expected, the spectra for these geometric operators are discrete. Okay? They come in distinct units, and they're the smallest unit. So the physical geometry defined in loop quantum gravity isn't as finely grained as we might think, as given to us by Riemannian or pseudo-Riemannian geometry. Okay? So I don't need to say anything else, maybe. So think of a manifold with lumps of geometry. So you got smooth like this table, you got lumps of clay on it. Perhaps this suggests that the manifold itself is granular, that the geometry is. Okay. Now what this suggests amounts to, I'm not quite certain how strong that suggests we're supposed to take that. Good. So that's one way. This is going to come up again. Okay. Now another effect of the geometric operators in loop quantum gravity is as follows. We have a region of spacetime, a region of the manifold, and we want to kind of approximate classical geometry well. So what do? We shove a whole bunch of spin networks, a whole bunch of loops with nodes into a particular region, hoping that we cram them in there, that we're going to squint our eyes and the geometry itself is going to look classical. Okay? But that doesn't happen. You toss a whole bunch of things in, and instead of approximating a given metric, the geometry produced by a given metric, you approximate a different one. In fact, oftentimes you throw more nodes in. Daniela, you can help me with this. You throw more nodes in, you might actually increase the sort of geometry of that region, not made it approximate the classical value. Okay. Now, in this context, Christopher Isham and Jeremy Butterfield suggest that this is the way one might go in terms of talking about the manifold itself coming into the quantization scheme, but kind of indirectly. I think that we could see something like this, and Chris, you could help me out with this, in both Chris's work and Karen Crowther's work. So, Chris, we'll say, I think Chris. So note that I said two things on the previous slide.
That was taken by a professional photographer.
It was candid. You were in your office. Okay, so note that I mentioned two different things. The first thing is that our area and volume operators are discrete, right? They only come in certain size lumps. Okay, that's one thing. The second thing is as we shove more of them into a particular area of spacetime, we don't get a better approximation for classical geometry. We get larger volumes or strange things happening. Okay. Now, with respect to this latter sort of effect, Chris says, oh no, not that one. Okay. So this quote here is with respect to what I just talked about. Pushing a bunch of things in, the quote-unquote lattice spacing, where the distances, the average distance between the loops is decreasing. Okay, so taking the classical limit, as he says, should have as its effect the re-emergence of the continuous space-time with its pseudo-Riemannian manifold. However, as he notes, it does not happen. Taking this limit does not change the structure from discrete quantum states to smooth manifolds. Okay? Now, with respect to the second thing, the fact that our spectrum of geometric observables are discrete, Christian concludes from that, thus, the smooth space of classical theory is supplanted by discrete quantum structure displaying the granular nature of space at the Planck scale. Continuous space, as we find it in classical theory, such as GR, as it figures in our conceptions of the world, is merely an emergent phenomenon. Okay, so I think that we see some of these things in Chris's work as well as in Karen Crowther's work, where having quantized a geometric structure somehow removes a sense in which we have a continuous space-time structure to begin with. Okay? Now, what the trickle-down effects actually amount to and how it affects this, it's unclear to me. But the point is, if this actually happens, we get two things. First off, we get a robust sense of space-time emergence, right? Because if it actually trickles down, then the manifold has been destroyed of the continuous manifold. You actually have something that is pre-manifoldy. Okay? We have the geometry that's already been quantized, so you have a thick sense in which space-time itself disappears and presumably will reappear in the emergence relations or the emergence limit. However, if you do that, then you no longer, this is what our state represents, right? Our state represents this structure, a sort of pre-geometric, pre-manifold structure, if there's actually these trickle-down effects. And if that's the case, then just like in TG, we don't actually have a well-defined sort of coordinate function that could ever represent time to begin with, right? We've messed up all the structure that we were using, again, in defining our constraints to begin with, right? So there's a sense in which time goes missing under this notion of space-time emergence. Okay? It's a very thick space-time emergence because the manifold gets involved in the process, right? And time is missing. Okay. So you said I have like...
Yeah, till 5. I mean, like
5.
4.
Yeah. Okay.
8 minutes.
Yeah, that's fine. Okay. So the next one I'm going to talk about is Cartesian dualism. No metric, no
That
time.
includes questions, by the way, so if you want some questions.
Oh, I don't want
Be
it.
judicious.
Okay. I should be able to get some questions in. Okay. So this one is like this. So Descartes said human beings are what? We are dual structures, so we need both minds and bodies, right? If you have a body but no mind, you don't have a person. If you have a mind but no body, you don't have a person, right? You need both structures. Now, one might think, what is space-time in GR? Space-time is a manifold plus a metric, you know? Do you have space-time if you just have a bare manifold? Do you have space-time if you just have a metric? Okay? Presumably not. Space-time is this dual structure, okay? This interpretation is as follows, okay? In loop quantum gravity, we just have a quantized metric field. Okay? You still have a classic manifold upon which your states or structures are defined. However, since you quantize the metric, you've destroyed the sense in which you have space and time. Because you removed one of the two components. Space-time is a classical metric and a classical manifold. We've quantized the metric, so now we just have a quantum, a sum over metrics. And so you keep the structure that you have when you're done with that isn't space-time. Whatever it is, it's not space-time. Though you still have a perfectly untouched classical manifold, it's not space-time itself. Another way to see this is, yes, we have an x-naught coordinate, right? But without a well-defined metric, we don't have any sort of causal structure on there. We have no time-like direction. We have no distances between points. You could find 2 points on that axis, but there you don't have any distance defined between them. So in what sense does this axis represent time? Okay? So under this interpretation, if you've thrown away the metric, you've thrown away time itself, insofar as the structure that's left over can't represent space-time. It still may be physical. It's some pre-space-time physical manifold, but it's not the space-time manifold. It's a manifold which will become space-time once you add the metric on. Now, if this is our interpretation, I kind of want to think, let's say that you're in DeWitt's office in 1967, and you're a really spunky sort of graduate student, and he comes to you and he says, look, I've derive this frozen formalism. And you say, well, I don't know, what's x naught? And he says, it's time. You're like, time? Why does x naught model time to begin with? Right? There's no metric structure on it. There's no causal structure on our manifold. In what sense should we think there's going to be dynamical evolution in a theory on a manifold that has no metric? So that's my intuition here. You might not share it, and I don't even necessarily endorse it, but it's a possible way in which time disappears and in which space-time emerges, right? So if the manifold itself was space-time, which I don't endorse, if the manifold itself was space-time and you quantize the metric, right? Well, then you don't say space-time emerges, right? You just say geometry emerges. You still have a manifold, right? But if you think that a classical metric is required for you to have this thing called space-time, then when you've quantized the metric, you've quantized, in a sense, you've quantized space-time. Space-time has disappeared from your structure, right? So as you take the classical limit, a classical metric emerges, you now have an emergent space-time with it, okay? But not because the manifold has emerged. The manifold has always been there. It's just waiting for the classical metric to come in to make it like a robust space-time or robust. So this is another way in which space-time can emerge in loop quantum gravity. I'm not actually endorsing any of these necessarily. I'm thinking about different ways in which space-time might emerge in loop quantum gravity and showing how in all four families you don't have anything like a time coordinate. Now note that though you don't have anything like a time coordinate in all these last three things, time is missing, and none of them did time go missing because of our considerations of the Wheeler-Dewitt equation, right? In none of these considerations did time go missing from our theory because of our interpretation of the Wheeler-Dewitt equation. Time went missing long before, and it was due to our interpretation of what space-time means and what it was that we were quantizing in our theory. I don't know what's left. Okay, if space-time emerges, then only one family is naturally related to the problem of time, that's Rovelli's. And in particular, if space-time emerges in all its manifold glory, play on words, then there is no problem with time. Okay, I don't think I have anything else. I guess I'll stop. Thank you.
Okay, we've got 5 minutes for questions now.
The question about the Rovelli, they're not going to require what the sense of emergence is. Why is it the case that the metric is emergent, but why can't he say, why doesn't he want to say that the manifold's emergent? I don't know, it seems like he just say, manifold's a useful thing. And it seems like there's a manifold, it's useful, it looks like a manifold, it's not their fundamental. So he's got this gauge argument, but I tend in the first place to think of gauge arguments is about what's there fundamentally. So he doesn't have to say the manifold's there fundamentally.
And yeah. So maybe I'm missing the question a little bit. I think that you're right. You would say the manifold's not there fundamentally.
So the question is, why do you say different things about metric and manifold? Neither of them are both fundamental, but they both make it useful for physics.
Did you say they're both fundamental?
Neither of them are fundamental, but they're both useful at
Yeah,
a
sure.
level. So what's it?
Yeah, so I think Rovelli would say that the manifold, I think he'd say the manifold is useful insofar as like Hilbert spaces are useful. They're not physical structures, they're just mathematical devices. There's no sense in which they're useful for our predictions of the world. So the metric is useful for our predictions of the world because we go out and we measure distances between things. Okay? But we don't ever require the manifold itself or some particular structure of the manifold to make predictions in the world. So yeah, in a sense, the classical metric isn't fundamental because we've quantized it. But in taking the sort of classical limit, we get it back and we're able to make predictions about the world. There's no sense in which the manifold in the classical regime or the quantum regime shows up in any sort of physical interpretations or physical predictions about the world. You're frowning, I may not have answered the question. Okay. No, I mean, yeah, I'm answering. I'm really putting words in his mouth. And let's pretend that these are words he would say. So if I'm wrong, it's because he was wrong.
David,
What about topology?
Yeah.
How are you going to live with topology?
Oh, I agree. I don't know.
Yeah,
I mean, maybe Daniele, you could help us with this. So the question is, you know, we've thrown out, there's a sense in which we use this gauge argument to throw away space-time. You know, space-time doesn't seem to be playing a role, but it seems like the topology of space-time would be important for,
Classical GR,
yeah,
the phase space is given by, let's say, let's forget about phase space. In the covariant language,
yeah,
the configuration space is a matrix compatible with a given global topology up to diffuse.
right.
The up to diffuse is exactly what removes any notion of points and coordinates and anything like that. But you still have a constraint on the class of geometries that form your possible configurations.
Given to you by the
Topological
topology.
constraints. So in that sense, we're still a remnant of the manifold we started
Got it.
from in global topological constraints.
Interesting.
But there's no manifold anymore because of difference in classical geometry.
Yeah, no, that's interesting. So in a sense, you're saying the manifold disappears in one sense because of
So you
because of
constrain the
diffuse.
class of metrics that you want to quantize,
By
and then you
using,
remove any notion of them being stuff on the manifold,
yeah.
and that's diffuse. But you still have a restricted class of geometries that you end up with after removing diffuse, not the most general geometry.
Right, so I think that, I don't know what your guys' intuition is, but my intuition is, since you still have a restriction given to you by the topology, and the topology is a structure
It's a
on,
global condition. It doesn't give you any time direction and
Yeah.
time variable. It's just,
yeah,
it's like you have a torus, a cylinder,
yeah,
but there's no notion of time or space in the torus or in the cylinder. That has to be reconstructed from the geometry.
yeah, okay. So we could keep talking about this point. I think this is actually an interesting discussion, but it might take us away from other questions if there were other ones.
Yeah, do you want to quickly?
Yeah, maybe it's the same question that other people have, but what is a metric without a manifold, or is there a metric space?
I think that is that mathematically you use a manifold to define the metric, but the manifold itself doesn't represent anything physical in the world. So just like you use a Hilbert space to define a vector, you know, in the Hilbert space, the Hilbert space itself isn't really showing up in terms of making physical predictions, other than constraining what your space of vectors look like.
What you quantize when you try to quantize GR is not metrics, it's geometries. And those
Sure.
are the equivalent class of metrics under diffuse.
Yeah.
Yes. That's the stuff you try to quantize. That's the stuff that forms your configuration space, not the metric. The
Okay.
metric is just a redundant object, which is the thing we're used to work with. So for convenience, we may introduce a manifold, put a metric on top, maybe even use coordinates, but that's not the configuration space of GR. It's not the stuff that you go about quantizing. So all this imposition of diffuse, hamiltonian constraint, spatial diffuse constraint, and so on, it's just the steps that are needed in order to get to the point in which you may try to extract some physics.
In the Hamiltonian
Before you do
Hamiltonian formula.
Yeah, or in the
In
path
any
integral,
formulation,
until if you have to integrate over geometries, not metrics. You may do that in steps. You write an integral with some measure over metrics, and then you try to mod out by four-dimensional diffuse. But until you have done that, you're not doing any physics. There's nothing physical there, exactly because you're still with stuff on a manifold with points, coordinates, and so on.
Okay,
It's nothing to do with canonical versus covariant. It has nothing to do with classical versus quantum. Just classical GR.
okay, we better stop. Let's thank Joshua.